Today, we are focusing on the static and dynamic performance of the CS stage. That's what we are going to design. And this will be done in a few presentations. And we will not consider, in the first part, we will not consider influence of source and load. We will just look at the stage driven under ideal conditions and terminated ideal conditions. So the first thing, and this is like we did it already, but let's do it step by step again, is that we will determine the bias sources. So we need requirements for the bias. So let's say we want to have a stage that can deliver a maximum negative output voltage excursion of 0.9 volt and a maximum positive output current of 10 microamp. I hope you remember why we choose this, because this was related to the biasing scheme we did in the previous lecture. And if you don't, then here it will be presented a little bit later. So we would also want to desire, for example, the transistor in strong inversion or weak inversion or whatever from let's say we will discover parameters to decide whether it should be in weak inversion or strong inversion. But let's say we want to have it in weak inversion and we want to have a kind of minimum geometry. And then we would come up with an idea, having a minimum geometry transistor like the CMOS 18 device with a width of 220 nanometer and a length of 180 nanometer. And we want to bias it such that it can deliver a negative swing of 0.9 volt set by the voltage source in the drain of the device and a current of 10 microamp set by the output current of 10 microamps that we have seen before. And the question, of course, is what do we have to apply at the input such that the output will be exactly at 0 volt and the input will be exactly at 0 volt. So we can terminate it with any DC impedance or VI characteristic and the operating point does not change. Passive, yes, with any passive termination. For all passive terminations, and the operating point is constant. You can short it, you can leave it open, you can put a non-linear resistor there. This would be still be 0, and that would still be 0. That is the idea of biasing. So what we then do is we are going to measure at the output. So how we are going to obtain the input values required for this drive capability for 0.9 volt and 10 microamp. We would simply measure the output that should be 0 and put a very large gain such as to control the device. So if we have 1K gain here, 1K voltage gain, then for example, if the FET would need 500 millivolts to produce this 10 microamps here, then we would have 500 microvolts error here at the input. And if you think this is too large, you just make the gain larger, then it drops. Actually, you would like to have a nuller there, but that would be bad for convergence reasons because there's a large dense zone and probably it doesn't work in your simulator. So this is then the way to determine the voltages across this controlled voltage source. You will then measure VGS and the current through the controlled voltage source will be the IG that you need to bias the device. So then we apply the bias sources. Let's do it. Here we have I determined them in LT Spice or in Spice, whatever version it is. I needed 0.61 and a lot of more numbers voltage here and 0 bias current. Although I need zeros, and that would provide me an error here of 631 microvolt because this is just like this one divided by about 1000 because of the loop gain that I have here of about 1000. The gain, sorry, of about 1000. So that is 0.1% inaccuracy, which for this purpose is good enough with me. This resistor, what is it doing there? Well, although we need a bias current of 0 amps there, 0, because the gate is completely isolated in the model, there's no leakage current as well. We need a path for charging it. That's one. So also in practice, you would need to have a path. Otherwise, this would be floating. You can have any charge on your gate, but it doesn't go to 0.61 volt. This should be 0 volt if there is 0 voltage. So there must be a current path to this one. And for this, to stress that it can be a very, very large resistor, I put just 1 tera ohm there, that it will be clear that you still have 0 at the output. And Spice cannot handle floating nodes. Some versions of Spice can, because this is not really but with not with the MOSFET, because this would be completely isolated. So that's why you also need for the simulation to put something there. So basically, this is the biased source as we have discussed it before, and all curves now pass through the origin. So here VIII is the input characteristic, input voltage current characteristic. VOIO is the output voltage current, the output characteristic, voltage to current. VIVO is the voltage transfer from voltage input to open circuit voltage at the output. This is the transadmittance from input voltage to short circuit output current. This is the transimpedance from input current to open output voltage, and the current gain from input current to output current.